more words about test design. The key things that we have to remember that we need to have for any drill stem test is proper functioning downhole tools, good conditioned hole, good DST design, and of course, the most important perhaps, is safe operating practices. Your manual covers in detail a number of aspects of the 4 items I've just mentioned. We should say a few words here, though, about certain aspects of test design. Specifically, the required cushion and how long the flow test is going to run, whether it be onshore or offshore, in order to get the proper information with which to make our analysis.
The initial flow of formation fluids into an empty annulus may result in a severe pressure shock, which in turn may cause an unseating of the packer. As a rule of thumb, if the differential pressure between the formation and the drill pipe is expected to exceed 4,000 psi, a water, nitrogen, or diesel cushion should be placed in the drill pipe to reduce the pressure differential to 4,000 psi or less when the valve is opened. This means that the hydrostatic pressure minus the pressure imposed by the cushion should not exceed 4,000 psi. The height of the cushion, then, should be planned with this in mind. For example, if the drilling fluid has an equivalent hydrostatic gradient of 0.48 psi per foot, and the formation to be tested is at a depth of 13,500 feet, we would estimate the water cushion needs as follows. The hydrostatic pressure is equal to 0.48 psi per foot, multiplied by 13,500 feet. The fresh water cushion is equal to 0.433 psi per foot times the height of the cushion. The difference of these two sums should equal or exceed 4,000. Solving this relationship, we find H to be 5,727 feet. A second design consideration is the duration of the shut-in and flow periods. It is important that the flow and shut-in periods of the test be long enough to obtain meaningful results. Rules of thumb, although not always to be followed, suggest the following test period durations. The initial flow period typically lasts for 5 to 10 minutes. The initial shut-in period, 30 to 60 minutes. The final flow period for an onshore open-hole test will normally be 60 to 80 minutes in length, depending on the expected permeability of the formation. For offshore cased hole tests, the final flow period may be restricted to daylight hours, typically 8 hours. The final shut-in period is usually 1.5 to 2 times the duration of the second flow period.
Of course, if the pressure is being measured at the surface in real time, then the test will be terminated at the point when we have sufficient data to make our analysis. If the test is being done offshore and there's sufficient daylight to run a second flow rate test, then that is normally performed. It's important to give your service company representative as much time as possible that you plan a drill stem test. A checklist of the information that that company would like to receive is contained in Section 5 of your manual. Now, let's go on with the interpretation of test results. We know that what we receive in a test is a plot, typically, of pressure versus time, a drill stem test chart. What we'd like to look at, first of all, is what all the markings on a drill stem test mean on this chart. And then we'll go on to discuss the qualitative interpretation of test results. And after having done that, we'll go on to the quantitative analysis of the data.
Here we see a pressure time plot for a typical DST chart. Note that pressure on the vertical scale increases upward. Time on the horizontal scale increases from left to right. Based on the convention of an individual service company or the design of a particular manufacturer's pressure recorder, the pressure scale or the time scale may be reversed. The manner of recording should not affect the final results, but we have to know which is which. Before the test assembly is run into the hole, the tester loads the chart into the recorder and draws the baseline on the chart using the recorder stylus. This represents 0 psig for the mechanical pressure gauge. The clock is then started, the tool assembled and started in the hole. From what we stated earlier, we recognize this to be a typical DST chart. A to B on the chart represents the buildup in hydrostatic pressure as the test tools are run into the hole. The line is not smooth because of pressure surges which occur as each connection is made, because of tight spots encountered in the open hole, or because of delays required to add cushion or repair surface equipment. After the tools reach the test interval, the surface equipment is connected to the drill pipe. During this time, the hydrostatic pressure stabilizes at point B, pressure surges end, and a value of the initial hydrostatic pressure is recorded at the point where there is a relatively flat pressure value. The packer is then set. The tool is opened, B to C, and the initial flow period takes place from C to D. This period lasts for about 5 to 10 minutes. The initial pressure recorded at point C is usually near atmospheric, unless a cushion has been placed in the drill pipe, or a highly productive formation is being tested, and it reacts quicker than the recording instruments can record. The tool is then closed, and the initial shut-in period, with a duration of 30 to 60 minutes, takes place from D to E. Surface indications of flow cease. The pressure builds up, approaching the static reservoir pressure at point E without the effect of supercharging. The test tool is then opened again from E to F, and the final flow period occurs from F to G. The shape of the buildup will depend upon the properties of the formation and the produced fluids. The duration of this period, as we mentioned earlier, will depend upon whether we are doing an onshore open hole test or an offshore cased hole test. At the end of the final flow period, the tool is shut in at point G, and the final buildup period takes place from G to H. The packer is then released at H. The hydrostatic pressure caused by the mud column is again felt by the pressure recorder, and the tool is retrieved from the hole from I to J. The chart is brought to the surface, and the data collected in either chart or digital form is now ready for interpretation. But before beginning the analysis, it is important to be sure that the data collected is valid and that the proper data are being used. To do this, we must check to see that a packer seal was maintained throughout the test. This may be verified by comparing measured pressures at 2 different recorders in the test string. We must also select the most representative pressure recorder from among those available for our analysis. If the pressure data or the packer seal is suspect, we should repeat the test. Otherwise, we begin our quantitative analysis.
All of the marks and the lines that appear on the DST chart mean something in a DST analysis. Whether it is the operation of the subsurface tool, the motion of the drill pipe or the tubing, or the operation of the surface control valve, the marking has some meaning. The only line that is not influenced by these operations is the baseline, which is placed on the chart at the surface. It is the difference then between this baseline and the profile of pressure versus time that we get on the DST chart that we look to in the qualitative analysis of our results. Let's look at a few examples.
It is possible to state the relative level of formation permeability within the region of the wellbore being tested. Charts from low permeability formations, as we see here, produce buildup curves that suggest the pressure is beginning to stabilize. This is often referred to as pressure starting around the curve. These formations have very low pressure increases, if any, during the flow periods. There will be a weak blow at the surface, small fluid recovery, and fairly low flowing pressures. Charts from average permeability formations exhibit better buildup curves during the shut-in periods and some pressure buildup during the flow periods. There should be a good blow description, moderate fluid recovery, and increasing pressures from one flow period to the next. Charts from high permeability formations will have a high flow rate and a strong blow, high flowing pressures, and rapid stabilization of pressure during buildup. The one shown here stabilized at the point where the flowing pressure is almost equal to the final shut-in pressure. Significant well-bore damage exhibits low flowing pressures, a sharp pressure rise after the tool is shut in, and a short pressure transition radius during buildup, followed by a flat pressure increase. There is a weak blow at the surface and very little recovery. Fluid depletion during the test is minimal. If the wellbore cleans up during the test, then there will be a change in the character of the curves from that shown here to one we just saw. The DST may also provide us with a measure of whether the zone being tested is large or small. The evidence we use is the pressure difference between the initial and final stabilized shut-in values. If a significant difference exists, we have a reservoir of limited or finite extent. We see such an example here. The fluids produced during the flow periods have caused a measurable depletion or drawdown of the reservoir. A pressure change of 1.5% or greater is considered serious, and retesting may be warranted. A reservoir barrier or nearby production may also cause the same effect, and so some additional analysis may be required. Here we see an excellent example of a decrease in pressure levels between the initial and final buildup periods. In this case, one caused by a reservoir barrier or permeability restriction as opposed to depletion. The change in the slope of the buildup curve indicates a reduction in transmissibility some distance from the wellbore.
A visual inspection of the DST chart will normally reveal what fluids were produced during the test. That is, whether gas, liquid, or both. Let's look at a few examples.
Here we see the situation when liquid is produced during the test. An increase in flowing pressures takes place. The pressure at the beginning of the final flow period will be equal to that at the end of the initial flow period, a value which represents the pressure caused by the column of recovered liquid in the drill pipe. If the liquid flows to the surface during the test, there will be an initial increase in flowing downhole pressure, followed by a surge as liquid reaches the surface. Thereafter, there will be a stabilization of flow rate and pressure. This chart also shows the reverse circulation procedures conducted after much of the drill string was recovered. It is also possible, as we see here, that liquid fills the drill pipe to a level where the pressure imposed by the hydrostatic column equals the reservoir pressure. The well kills itself and flow stops.
When gas, as opposed to liquid, is produced during the drill stem test, the characteristics of the chart are quite different. Gas is normally produced at a relatively constant downhole pressure, bottom hole pressure. This is normally the case unless gas is being produced at such a high rate as to cause a back pressure on the formation.
In some cases, as we see here, the flowing pressures will actually decrease during flow. Flat or slightly decreasing flowing pressures, then, are the indication of gas production. The presence of pressure fluctuations during flow, as we see here, is an indication that both liquid and gas are being produced. These fluctuations, for example, were caused by gas unloading slugs of liquid at the surface. The fact that a liquid cushion was used may also be observed. A water cushion is shown in this chart. The cushion was added to the drill pipe here, as the drill pipe was run into the hole. When the tool was opened for the initial flow period, the pressure dropped to that imposed by the cushion, rather than atmospheric pressure. If a nitrogen cushion is used, nitrogen is pumped into the drill pipe to the desired pressure before the flow control valve is opened. The valve is then opened and the nitrogen bled off slowly at the surface to allow the test zone to begin flowing, thus producing a somewhat different chart.
Plugging of the test tool, whether at the anchor, within the test tools, or at the surface, may also be indicated on the DST chart. The degree of plugging, whether complete, partial, or gradual unplugging as the test continues, is also observable. Let's look at a few examples, but in doing so, note that we use the pressure difference between an inside recorder and an outside recorder to indicate the degree of plugging.
These charts, showing both the inside and outside recorders, indicate that the anchor was beginning to plug during the initial flow period and became completely plugged just after the onset of the final flow. We are convinced of this because there is no pressure buildup during both the flow and subsequent shut-in periods on the inside recorder, though the outside recorder continues to feel the formation pressure. This is the expected response of a plugged anchor. On the other hand, if the tool becomes plugged above the inside recorder during the final flow period, as we see here, both recorders are exposed to the same buildup pressures after the final shut-in period.
As you can see, the qualitative interpretation of the DST chart provides a great deal of information to us in the overall evaluation of the test. This is especially so when pressure is being measured in real time at the surface, and the opportunity exists to retest the zone without adding a great deal of additional time or cost to the test. Before going on then to the quantitative interpretation of test results, let's take a few minutes and ask you to work exercise 3. In the meantime, now that it's getting darker here at the test site, I'll go back up on the rig floor and see how they're progressing. As I left you at the end of Unit 3, I went over and talked to the tool pusher, told me we're still having a great deal of difficulty cleaning up the hole, conditioning it, so we decided to go home for the night and come back this morning. Early this morning, they finally got the drill pipe and drill collars out of the hole, put the test tools on the bottom, and they've started the tools back in the hole. So the test is closer to reality than it was last night, but we still have a little bit of time to spend before we see the pressure data coming to us during the test itself. So in Unit 4 now, we'll go on and discuss the quantitative analysis of drill stem test data. We really have two choices to follow. One of them by looking at the pressure transient analysis techniques developed in the 1950s and 1960s, which are usually called the conventional pressure transient analysis methods. Or we can go on and use the more modern techniques developed in the 70s and the 80s, referred to as modern well test analysis, in our interpretation of data. We can couple each of these with the equations that represent inflow performance, vertical lift performance, and the performance of flow-through surface equipment to come up with an optimal design for our production well system. In this module, we'll cover all three of these aspects: conventional well test analysis, modern well test analysis, and the optimal design of a production system for our well. I might caution you at the outset, though, that if you don't have the background in these qualitative analysis techniques, refer to the earlier modules in well testing analysis.
The conventional well test interpretation methods are based upon an idealized wellbore reservoir flow model. The basic model assumes a homogeneous reservoir of infinite lateral extent with impermeable upper and lower boundaries and uniform initial pressure throughout. The inner boundary condition, that is, the conditions at the wellbore, is one which allows the well to flow at a constant rate for a period of time and then to be shut in. The inner boundary conditions for this model also allow for skin to exist near the wellbore. The outer boundary condition normally provides for a constant pressure and infinitely large distance from the wellbore. Using this rather simplified model for our wellbore reservoir flow system, we may solve the appropriate radial flow equations for the test well. Their solution in graphical form is what Horner and others have given us to quantify the results of DSTs and other well tests. For oil wells, a plot of the bottom hole pressure, P sub WS, during pressure buildup versus T sub P plus delta T over delta T should yield a straight line on semi-log paper. T sub P is the time of flow prior to shut-in, and delta T is the elapsed time since shut-in. Note that a straight line does not normally exist during early times because of the wellbore and near wellbore effects of skin, wellbore storage, turbulent flow, multiphase flow, partial penetration, and so forth. Once we have prepared the Horner plot of the pressure buildup data of a DST, we may extrapolate the plot to obtain the initial reservoir pressure and calculate the transmissibility, flow capacity, formation permeability, the skin factor, the damage ratio, the productivity index, and the radius of investigation. Let's begin with the determination of the initial reservoir pressure. For a reservoir of infinite radial extent, it can be shown that the extrapolation of the straight line of the Horner plot to a value of T sub P plus delta T over delta T equal to 1 will give the value of the initial reservoir pressure, P sub I. In the event that the reservoir is of finite extent, the extrapolated pressure is referred to as P star and is less than the original pressure after some depletion occurs. Now let's see how transmissibility is calculated. Transmissibility is a measure of the ability of the reservoir to transmit fluids. It is defined as the effective permeability of the flowing phase, here assumed to be oil, multiplied by the formation thickness, divided by the viscosity of the flowing fluid. It can be shown to be equal to 162.6 multiplied by the average flow rate during the preceding flow period, Q sub O in barrels per day, multiplied by the formation volume factor, B sub O, divided by the negative slope value of the slope of the straight line on the Horner plot, M, in PSI per cycle. After measuring M, all terms on the right side are known, and the transmissibility can be calculated. The flow capacity of the test zone is equal to the effective permeability multiplied by the formation thickness. It is calculated by multiplying the transmissibility by the viscosity of the produced fluid at reservoir conditions. The average effective permeability of the reservoir to the flowing fluid, in this case oil, is calculated by dividing the flow capacity, K sub OH, by the estimated thickness of the test zone. Note that this value of permeability is measured under dynamic conditions, and its value depends on the value of the slope, M, the formation thickness, and the oil viscosity. The skin factor, S, is a quantitative measure of the damage or enhancement to the formation that exists in the immediate vicinity of the wellbore. A positive value of S indicates damage, for example. A negative value can indicate enhancement. In order to calculate the skin factor, we must know the value of the slope M, the flowing bottom hole pressure just as the well is shut in, that is at delta T equals 0, and the bottom hole pressure 1 hour after shut-in. We obtained this value by extrapolating the straight line to a value of delta T equals 1 hour. Knowing these values and other rock and fluid properties, we can use equation 5 in your manual, shown here, to calculate a value for the skin factor S. The damage ratio, DR, is the ratio of the well's potential flow rate without skin to the rate actually measured during the test. If damage exists, DR will be greater than 1.0. If the well is stimulated, DR will be less than 1.0. The productivity index, or PI, of a well is the ratio of its actual flow rate to the drawdown at that flow rate. These terms in this relationship are familiar to us. The PI provides a means of comparing wells and a way of predicting inflow rates for the test well at other drawdowns. The final item on our list is the radius of investigation, which we define as the radial distance from the well where the original pressure has been significantly affected by production into the well during the test. Provided the reservoir is not finite or barriers to flow do not exist, the radius of investigation at a given time t may be calculated with some precision using this relationship. Note that t is the cumulative flowing time in hours, and the radius of investigation is in feet. We observe that the radius of investigation depends on the time of flow and rock fluid properties and not on flow rate.
We have assumed during our discussion so far that the average flow rate during the flow periods may be either calculated or measured. We should say a few words about how this is done before looking at a few examples.
There are two options for estimating the flow rates during the DST flow periods, and they depend upon whether or not the well flows to surface during the test. Let's consider first those wells that do not flow to surface. We estimate the fluid volume produced during the flow period by noting the bottom hole pressure change, delta P, that occurs during the flow period, then estimating the height of rise of fluid during this same period, and finally converting this value to a fluid volume in barrels. The increase in the height of rise of liquid in the drill pipe is equal to delta P divided by the hydrostatic gradient of the produced fluid. The units here are in feet. The volume produced then will be equal to H multiplied by PC, the pipe capacity, the volume per foot of the tubular goods. Note that the produced volume is measured in stock tank barrels because gamma sub F, the specific gravity of the produced fluid, is given at surface conditions. To obtain the average production rate, we divide the volume produced by the time of flow. With T sub F, the time of flow in minutes, this relationship gives us the flow rate in stock tank barrels per day. Of course, if we have both drill collars and drill pipe in the hole, we must account for their different diameters in estimating the volume produced during the test. For wells that do flow to surface, we estimate the average flow rate by metering production as it passes through the separator. This may be done either continuously or periodically. Alternatively, we may retain the produced fluids in a tank. The average flow rate in stock tank barrels is the volume produced divided by the time during which production at the surface took place. In both cases, the measured volumes must be corrected for BSW, or basic sediment and water content, temperatures different than 60 degrees Fahrenheit, meter correction factor, and any shrinkage that occurs after metering.
In this unit, we have shown you how to calculate the various parameters that are available in DST analysis. Before going on to the conventional methods of analysis, let's stop and work exercise 4 in your manual.
Now let's see how a conventional drill stem test analysis is undertaken in practice. The well we are going to look at is an actual wildcat well drilled in the Williston Basin. The formation
Tested was the Duperow. The reservoir properties that we will calculate are those that we introduced in the last unit and for which you made calculations in exercise 4. Let's begin by listing the known data.
The tested interval was 11,456 to 11,494 feet below the Kelly bushing. The test string had 10,636 feet of 5-inch drill pipe and 812 feet of drill collars. We note their respective IDs. The oil gravity is 41 degrees API. Its viscosity is 0.21 centipoise. The porosity is 20%. The total compressibility is 17.7 times 10 to the minus 6. B sub O is 1.58, H is 7 feet, and R sub W is 0.36 feet. We are provided with complete pressure time data for both flow and shut-in periods. An initial flow period of 14 minutes was followed by an initial shut-in period of 92 minutes. The final flow period lasted 88 minutes, and this was followed by a final shut-in period of 251 minutes. This data was recorded electronically downhole and printed out at the surface and is reproduced in your manual. We are also told that a 2,984-foot water cushion was added to the drill string to prevent damage to the test string or unseating of the packer. The first step is to estimate the average flow rates during both the initial and final flow periods. This well did not flow to surface, so we must estimate the flow rate indirectly through the pressure differences that occur during the flow periods. Taking into account the pressure imposed by the water cushion, we calculate the pressure increase, delta P, caused by the produced fluid during the initial flow period to be 380 psi, and during the final flow period to be 852 psi. Using the specific gravity of this 41-degree API oil, we calculate the increase in the height of the fluid level during each flow period. For the initial flow period, we find it to be 1,070.4 feet, and for the final flow period, 2,400 feet. Now we must calculate the volume of fluid that these fluid columns represent. At the bottom of the drill string, we have 812 feet of drill collars, which hold 0.00607 barrels per foot of length. And above them we have drill pipe, which with its larger ID, holds 0.01773 barrels per foot of length. Knowing the incremental height of rise of fluid during each flow period, and the location of the drill collars and drill pipe, we calculate the volume of fluid added to the drill string during each flow period. This turns out to be 9.51 and 42.55 stock tank barrels, respectively. We divide these values by the time of flow for each flow period, that is 14 and 88 minutes, respectively, and obtain the average production rates, Q sub O, of a little over 978 barrels per day for the initial flow period and 696 for the final one. These values are quite different and probably reflect the longer flow time and better test conditions of the final flow period. We have more confidence then in the second production rate. The next step in our analysis is to prepare Horner plots for the two build-up periods. We plot the data points for both the initial and final build-up periods as shown here. Now we draw smooth curves through each set of points. With the information provided or graphically measured from the Horner plots, we obtain the following values for both the initial and final periods. The duration of flow during the initial period is 14 minutes, and for the second is the summation of 88 and 14, or 102 minutes. The flowing pressure at initial shut-in is 1,440 psi, and for the final shut-in period, 2,436 psi. The straight line slopes on the Horner plots are 805 and 560 psi per cycle. And the pressure after 1 hour of shut-in is 5550 and 5375 respectively. With this information, we are in a position to begin our calculations. We are now prepared to perform the calculations that we discussed in the last unit. The first item in the list is the average reservoir pressure. To obtain its value, we return to our Horner plots and extrapolate the straight lines to their values at T sub P plus delta T over delta T equal to 1. This gives us values of 5,625 and 5,620 psi respectively. Let's maintain this information in a table as we proceed with our other calculations. Our next calculation is the transmissibility, which we remember is given by this relationship. Substituting values for flow rate and Horner plot slope, We calculate values of about 312.2 millidarcy feet per centipoise for the initial period and 319.4 for the final. Again, we note that these values are quite close. We enter these into our table and continue. The next item to calculate is flow capacity. It is equal to the transmissibility multiplied by the viscosity, mu sub O. The viscosity is known either from laboratory measurement or from existing correlations. In this case, we know it is 0.21 centipoise, and so we quickly calculate values of 65.6 millidarcy feet for the initial and 67.1 millidarcy feet for the final period. We add these values to our table and now calculate the effective permeability to the flowing phase, in this case, oil. It is equal to the flow capacity divided by the formation thickness, h, which we are told is 7 feet. Making the appropriate calculations, we find the values of K sub O from the initial period data to be 9.37 millidarcies, and from the final period to be 9.6 millidarcies. We enter these values into our table and move on to calculate the next term, the skin factor S. We remember that it is given by this relationship, and note that all terms on the right-hand side of the equal sign are known to us. We proceed to make the calculations of S for each flow period data, and find it to be 1.23 for the initial period and 0.785 for the final. We know that damage exists because both values are positive, but since the value decreased from the initial to the final period, we are inclined to suggest that some cleanup occurred during the final flow period. Because the value is now quite small, stimulation of this well is probably not going to be very helpful. We enter these values into our table and calculate the next term, in this case the damage ratio, dr. We remember its definition and note once again that the terms on the right side are all known to us. We calculate the damage ratios to be 1.26 and 1.15 for the initial and final periods respectively. We list them in our table. Now we are in a position to calculate the theoretical production rate for this well, that is, where no damage or stimulation exists. It is equal to the damage ratio multiplied by the actual production rate for the period. Substituting our calculated production rates for the two flow periods, we find the theoretical production rates to be 1,234 and 801 stock tank barrels per day, respectively. Here again, we note the sizable difference between the values for the two test periods and have confidence in the second value for reasons we mentioned earlier. We enter the DR and theoretical production rates into our table. The next to last calculation is the productivity index, a relationship which is quite familiar to us. It is the actual production rate during a flow period divided by the drawdown. We find it to be 0.234 stock tank barrels per day per PSI for the initial flow period and 0.219 for the final. We should use the second value in any of our inflow performance calculations. We add these values to the table and calculate the last item in our list, the radius of investigation. We remember how it is calculated and note that it depends on rock fluid properties and the time of flow. We enter values for each flow period and find the radius to be 55.7 feet for the first flow period and 141 feet for the final period. A larger radius and therefore a much larger reservoir volume was being analyzed during the second flow period. Once more, our confidence in the accuracy of the data for the final test period is reinforced. Had we extended the test to, say, 8 hours, the radius of investigation would have increased to about 330 feet. With this much larger volume of reservoir being tested, you'll understand the reason for the larger test periods offshore. Finally, we add the values of R sub T to our table.
We would conclude that the Williston Basin well could very likely be economical based on the data we've just calculated, provided there are markets nearby and provided the additional cost of stimulation is not needed. We could have also used this data to develop an optimal design for our subsurface and surface system, a technique that we'll show you how to conduct a little bit later in this module. For now then, please work exercise 5. The exercise that you're about to do is the data for the discovery well on the prospect that is here behind us. It is for an Ector County wildcat drilled some distance west of Odessa. Well, while you're working exercise 5, I went over to see how they're doing with the tools running in the hole, and they tell me they're almost on bottom. So they'll soon be hooking up the surface equipment and begin the test. Well, now that you understand the basic elements and procedures used in the conventional analysis of DSTs, let's go on and talk about the more recent developments, the developments of the 70s and the 80s. A great deal of detail is available to you in Module 401 on this subject, but some information must be presented here just to give you a summary of these techniques.
Modern methods allow us to define the reservoir flow system in greater detail. We may now distinguish the internal reservoir structure, such as natural fissures or multilayers, wellbore characteristics, such as fractures or partial penetration, and wellbore storage effects. We are able to make these distinctions because we are now able to describe mathematically a number of different reservoir and wellbore conditions. For example, we may consider the reservoir to be homogeneous, or to have a fractured or dual porosity system, or to have a multilayer system with or without cross flow, or finally to have a composite of several of these different reservoir flow systems. The wellbore conditions that may be considered in our mathematical description include skin effects, fractures, and partial wellbore penetration. The outer boundary of the reservoir affecting flow into the reservoir is considered either not to have flow or to be at a constant pressure. The interpretation procedure requires that we first use the actual test data to select the reservoir model. We then use the reservoir model selected to simulate the conditions of our test. We then compare the simulated data with the actual test results. If a good match of pressure profiles for both the actual and simulated test is obtained, we have the confidence that the reservoir model gives a reasonable description of the wellbore reservoir system. If not, we select another model and begin again. Now let's see how the appropriate reservoir model is selected. Using actual test data, we plot the change in pressure, delta P, during a pressure buildup period, probably the final buildup period, against the buildup time, delta T, on log paper. This plot allows the characteristic shape of the pressure response to be seen. Its shape allows us to identify the dominating flow regimes, and thus is referred to as a diagnostic plot. At an early time, period 1, the shape of the curve indicates the relative influence of wellbore storage effects. Period 2, the influence of near wellbore effects, such as fractures, partial penetration, dual porosity, and multilayer communication with the wellbore. Period 3 indicates whether we have a homogeneous or heterogeneous reservoir. And the shape of period 4 indicates the nature of the outer boundary condition. Specific details of the interpretation are given in Module PE 403. However, for illustration purposes, let's look at several different diagnostic plots. Here, for example, we see the pressure time plot for a well with wellbore storage in a closed homogeneous reservoir. With a change in the shape of the diagnostic plot, we interpret a well with wellbore storage and a low conductivity fracture in a closed homogeneous reservoir. And by once more changing the shape of the plot, we distinguish a well with wellbore storage in a heterogeneous reservoir of infinite lateral extent. We are thus able to use the pressure buildup data to define the needed reservoir model.
The only problem facing us is that every test will have a different level of delta P and delta T. We have to find an approach then that will make our analysis independent of the properties or characteristics of each individual well. The industry has found a way to do this through the use first of dimensionless variables and secondly through the use of type curves.
Type curves are log-log plots of dimensionless pressure, P sub D, versus dimensionless time, T sub D. Note that P sub D, T sub D, and C sub SD are dimensionless variables. C sub SD is the dimensionless wellbore storage term. As we shall see shortly, each dimensionless variable is defined in terms of the specific wellbore and reservoir system being tested. A set of type curves is available for each different reservoir model. Thus, for a reservoir model with wellbore storage, skin, and a reservoir exhibiting homogeneous flow behavior, we obtain this set of type curves. Each curve has a different value of C sub SD, e to the 2s, with the higher values above and lower values below. The higher values represent a region of wellbore damage, and the lower values a fractured well. Note that the approximate start of radial flow can be estimated. The presence of wellbore storage is exhibited on this plot by a straight line of unit slope at early time. We remember that this set of type curves has been obtained by mathematical simulation of a well test on our reservoir. We now have a procedure to follow in interpreting pressure buildup data. Let's use an example to show how it's done. First, we prepare the diagnostic plot of the log delta P versus log delta T during the pressure buildup period. In this case, because of the unit slope at early time and a straight line at later time, we have identified a model with wellbore storage, skin, and radial homogeneous flow. Using this plot, we identify the dominating flow regimes and specify the appropriate reservoir model. We then select the type curves which represent this appropriate reservoir model. The diagnostic plot is now superimposed onto the type curve to obtain a match point. The initial match is made. We do this by sliding the diagnostic plot over the type curve, aligning the straight line at early time, and selecting the best possible match curve. In this specific example, the match point occurs along the vertical axis at P sub D equal to 1.79 and delta P equal to 100, and along the horizontal axis at T sub D, C sub SD equal to 14.8 and delta T equal to 1. Once a unique match point has been obtained, we use the match point data and rearrange the dimensionless variables to calculate flow capacity, the storage coefficient, and skin factor. The equations are shown in your manual. We now compare the results using the Horner plot with those obtained using the type curves, specifically the values of K sub OH and S. A good comparison gives us confidence in our definition of the reservoir flow system, and with it we obtain a measure of the wellbore storage contribution. If we apply this approach to the test data obtained in our Williston Basin well, as we have done in the manual, we find that the data points during the buildup periods are characteristics of radial homogeneous flow with wellbore storage and skin. Superimposing the diagnostic plot over the appropriate type curves for the initial and final buildup periods, we obtain a match point for each period. With the match point data, we are able to calculate the flow capacity and skin effect for each flow period and compare these values with those obtained using the conventional information methods. The values for both the initial and final buildup periods indicate good agreement. We conclude that the modern form of analysis reinforces the results obtained earlier. The skin effect in both cases is lower during the second flow period. Incorporating wellbore storage effects into our calculations, as we do with modern analysis, gives a small positive skin factor of 0.59.
It is possible for us to use our data to go one step further, to develop an optimal flow system for our well. We do this by beginning first with a calculation of inflow performance, using the procedures we discussed in Module 102 in this series of petroleum engineering.
Doing this for our Williston Basin well, for example, we obtain plots of bottom hole pressure versus production rate at various average reservoir pressures as shown here. We see that the inflow performance curve shrinks as the reservoir is depleted and as the average reservoir pressure decreases. To the inflow performance curves, we now add tubing intake curves, those curves which represent, for various production rates, the cumulative pressure drop that occurs in the flow system as the production travels from the wellbore, up the tubing, through the wellhead and choke, gathering lines, surface equipment, and finally reaches the stock tank. The intersection of a tubing intake curve and the inflow performance curve indicates the system production rate for this size tubing and other assumed conditions. Each tubing intake curve represents a different flowing wellhead pressure. Thus, if the flow system has a flowing wellhead pressure of 100 psi, the production rate will be 332 BLPD. If the flowing wellhead pressure increases to 700 psi, the flow rate will drop to 260 BLPD. The Williston Basin well's production rate will decline with the average reservoir pressure from 332 barrels per day at 5,627 psi to 172 barrels per day at 3,000 psi.
We see then that in addition to providing us with valuable information about formation properties, the DST data may be used with computer models to simulate the overall well system. Using these models, we can develop an optimal design for the subsurface and surface equipment, both for the well's early life and for the way it will perform later in its productive history. Before summarizing the results of this total module, let's go over and talk about the test results here at this well. The test was undertaken just recently. The results are available, so let's go over to the service company van and see what those results are. Well, here we are in the service company van, in this case the Flow Patrol Johnston SPRO van system, SPRO meaning the surface pressure readout system. The test now is just about complete. The first flow period lasted for 5 minutes, then was followed by a shut-in period of an hour, a final flow period of 1 hour, and a final shut-in period of 2 hours. We've now entered the early evening, and with us is the man who has handled the interpretation of the test, Joey Doan, the Schlumberger service engineer. Joe, thank you for allowing us to come in your van and share the results of this test with you.
You're very welcome.
Joe, what's the first thing you normally do sitting in the van here with the test results?
First thing that I do during the test is to determine, after the flow period is ended and the shut-in has started, that we run the shut-ins long enough for us to determine whether or not the data that we are acquiring is in the semi-log straight line portion. This is done by making a log-log plot. Then we take the log-log plot and match it on our type curves. This allows us to determine that the data is in the semi-log straight line portion.
So with that done, you know you can terminate the test and go on and analyze the data itself.
Yes, sir. If the test were to be terminated at that point, we would know that the data that we have obtained is valid and can be used to get a good, reliable analysis.
Right, and your analysis is done in what fashion?
We use two methods. One, we use the log-log plots with the type curves and a semi-log plot or Horner analysis. These are checking type systems. One is used to check the other. Once we have determined that we are in the straight line portion on the log-log plot, then we know that the Horner plot that we are making is valid.
And you've done a Horner plot here in the van, have you?
Yes, sir. We have made the Horner plot.
All right. And you have a drill stem test chart, too, as well to look at, do you?
Yes, sir.
Could we look at that now and share that with us?
Okay. We have the plot right here on our plotter.
Give you a little hand here holding it.
Okay. This is our Cartesian plot. This is the same type plot that our mechanical recorder makes. It is made right here in real time at surface. We are able to determine right now that we have a good mechanical test, that we're not having some problems downhole that would cause us to have to rerun this test. From this chart, we are able to get 8 important points. We're able to determine our initial hydrostatic, the beginning and end pressure of our flow period, the final shut-in period from our first shut-in, the beginning and end pressures of our final flow, the end pressure from our final shut-in, and the final hydrostatic. We're also from this plot, we are able to give a visual interpretation. From this visual interpretation, I can determine whether or not the shut-ins were long enough, whether they have stabilized. From the shape of the shut-in curves, we're able to determine that we have wellbore damage. We're also able to tell that our packers held throughout the shut-in periods. We're able to determine from our flow periods on this chart that we did achieve a good formation sample.
Very good. You also then took the data during the build-up portions and with your Horner plot made some calculations of formation properties, did you?
That's correct.
Could you share those with us too, Joe?
Yes, I can. From the Horner plot and from the Horner analysis, we were able to determine that we had a transmissibility of 176 millidarcy feet centipoids. We were able to determine that we had 78.8 millidarcy feet for a productive capacity. We were able to calculate our permeability at 7.8 millidarcies. We were able to calculate a damage ratio of 1.8. We were able to calculate a pressure drop due to damage of 589.27 pounds. We were able to calculate a skin of 2.94, and also the radius of investigation was calculated at 17.79 feet.
So this well still has a pretty good sized skin factor.
Yes, sir.
Which stimulation might help to alleviate. If that were to occur, how about this well? Do you think, in your opinion, the operator is going to want to complete it?
Yes, I do. Even with the damage that is present, I believe this will make a very good well.
Well, that just about wraps up all of this module. It's been a long one, so let's take a few moments to summarize where we've been. We first of all pointed out the relationship that drill stem test data and results have in the evaluation of formations. We saw how it fits in along with other methods to make the decision as to whether you're going to complete or not complete a well. We looked at the surface and subsurface equipment in some detail, and then went on to test design and field procedures. After that, we talked about the drill stem test chart itself, and then its interpretation, both qualitatively and quantitatively. In the quantitative side, we saw that there was both the original conventional interpretation methods and the more modern interpretation procedures developed in the 70s and the 80s. Finally, we showed how either one of these could be coupled with a system analysis so as to develop an optimum design for our flowing well system. Before closing, let me ask you to work exercise 6 in your manual. And at the same time, take a look at the case studies that are in the back of the manual. These case studies, for those that are working in SI units, have those specific units for one or two of the case studies. Well, let me wish you then good luck. Thanks for watching. Good testing.
Oh, we're almost there. It's right around the bend.
Yeah. Is this your first time in the field, Paul?
Uh-huh. I've seen some movies and read about operations, but I've never seen it firsthand.
Okay. Now, this well here has just been completed.
Hey, why don't we park over there, Peter?
Oh, okay. Got a quarter for the meter? Let's go.
What's the first step?
Well, why don't you two go over to the mud house, take a look at some logs and cuttings, you know? I think they may have some relevance for you, Paul, since the acreage you'll be working has been leased nearby. Okay, I'm going to go speak to Dino, the tool pusher.
Catch you later.
How big do you expect this well to be?
Well, we're testing about 500 barrels per day from a gross pay interval of 100 feet. And, well, geophysics told us that we might find a pretty good trap here. Bingo, at 12,500 feet, we hit it.
Why here?
Well, this area seemed to satisfy the 5 conditions necessary for a commercial accumulation of oil and gas. Come on.
First, you need a mature source rock, usually an organic rich shale, but it could be a carbonate or coal. And it must be mature, cooked hot enough and long enough for the organic matter to be converted into petroleum. Second, there must be a migration path between source rock and the reservoir. The third factor is a reservoir rock that has both good permeability and porosity. Fourth, there must be an impermeable seal or cap rock above the reservoir. And finally, the source, reservoir, and seal must be arranged so that the hydrocarbons are trapped.
So if any of these 5 conditions isn't met, well, the petroleum prospects for an area won't be too good.
So is it all right to use the terms petroleum and hydrocarbons interchangeably?
Well, I guess so, but, well, strictly speaking, they're not quite the same.
Hydrocarbons are chemical compounds containing only the elements hydrogen and carbon, but petroleum contains other impurities. A fairly typical crude oil will contain about 85% carbon, 12 to 14% hydrogen, and the rest is mostly nitrogen, sulfur, and oxygen. And we also use the term hydrocarbons when talking about the products refined from petroleum. Petroleum, however, is a natural mixture of hydrocarbon compounds, just as it comes out of the reservoir. It can commonly occur in any of the 3 states of matter, as natural gas, as liquid crude oil, and as a solid or semi-solid tar.
Don't some change from one state of matter to another?
Oh, yeah. Petroleum in the reservoir is at elevated temperatures and pressures compared to the surface.
Some hydrocarbon compounds that are part of a single gaseous subsurface phase condense to a liquid when they're produced, condensates. Now, crude oil under pressure also contains dissolved gases, some of which may be released at lower surface pressures and produced as natural gas.
So, is this an oil or gas well?
Both, actually. Since the gas-to-oil ratio is high and the gas is sweet, now, generally we'd flare the gas, but since we're near a pipeline, we won't bother.
What do you mean by the gas being sweet?
Well, sweet gas means that it has a low hydrogen sulfide content. Sour gas has a high content. And sulfur, whether it's in sour gas or high sulfur crude oil, is an undesirable component because it causes corrosion and a lot of production problems. Let's take a look at some of the basic elements of petroleum chemistry.
Although hydrocarbon compounds consist only of the 2 elements hydrogen and carbon, there are a vast number of ways in which the atoms can be arranged. Hydrocarbon compounds can be grouped into series, of which 4 are particularly important in petroleum: the paraffins, naphthenes, aromatics, and resins and asphaltenes. Paraffins are usually one of the most abundant groups present in natural gas and crude oil. They form simple, chain-like structures with a general formula CnH2n plus 2. In paraffins, N, which we call the carbon number, can range to over 40. The simplest paraffin, with a carbon number of 1 and the formula CH4, is the hydrocarbon gas methane. Natural gas hydrocarbons are composed almost entirely of paraffin series molecules, particularly methane. A nearly pure methane gas is called dry gas. But all paraffins up to carbon number 5 are gaseous at normal temperatures and pressures. A natural gas with a considerable amount of these higher carbon number gases is called wet gas. Paraffins with carbon numbers higher than 5 are normally liquid crude, but as the carbon number increases beyond 15, paraffins become increasingly waxy and viscous and may have to be heated during production in order to flow. Naphthenes form as closed ring structures with a basic formula CnH2n. Compounds of the naphthene series have chemical and physical properties similar to paraffins that have the same carbon number. And naphthenes, together with the paraffins, form the major components of most crudes. The aromatics are the third group and have a structure based on a hexagonal ring of carbons with alternate single and double bonds. This basic unit is called the benzene ring, after the simplest and most abundant aromatic compound, benzene. The fourth group, the resins and asphaltenes, are complex compounds whose structures are basically a network of fused benzene rings. However, they're not pure hydrocarbons and contain small amounts of impurity atoms, mainly nitrogen, sulfur, and oxygen. As a result, they're sometimes called NSO compounds. Resins and asphaltenes are the heaviest components of crude oil and the major components of many natural tars and asphalts. We classify crude oils by their relative enrichment in these hydrocarbon groups. Here's one method proposed by Tissot and Velti, which plots paraffins, naphthenes, and the combination of aromatics in the NSO compounds as 3 axes of a triangular graph. A crude oil composition plots as a point on this diagram, and its position depends on the proportion of the 3 end members. Most crude oils lie within this central band on the triangle, but they can fall within certain delineated fields. Geologically old crude oil from the Paleozoic age rocks of North Africa is enriched in the paraffin end member and lies within the field of the paraffinic oils. This crude oil from the North Sea contains nearly equal amounts of paraffins and naphthenes, but together they make up more than 50% of the total composition. Crude oils falling within this field are therefore called paraffinic naphthenic oils. This crude from the Arabian Gulf has nearly equal amounts of paraffins and naphthenes, but together these two components make up less than 50% of the crude. The dominant components are the aromatics and the NSO compounds, so oils within this field are called aromatic intermediate oils. Heavy degraded oils are the most enriched in aromatics, resins, and asphaltenes. Some may contain naphthenes, but the paraffin content is always very low. While degradation by bacteria and by fresh meteoric waters of surface origin causes an oil to become heavy and asphaltic, thermal alteration and deep burial makes an oil lighter and more paraffinic.
Sure sounds complex.
Well, it is. The petroleum chemistry is a critical factor in production efficiency at the well. It'll also determine the amounts and kinds of refined products that you're going to end up with. Besides, these compounds are simple compared to the composition of kerogen.
Kerogen? Isn't that the organic matter in black shale?
Well, basically, yes, but let's find Wendy first, and I'll explain on the way.
Okay.
Now, kerogen is organic matter that's intermediate between the original source material and oil and gas. So it's not quite the same as the molecules of living organisms.
Like carbohydrates, fats, or proteins?
Right. Now, carbohydrates, fats, and proteins are complex biological molecules that first break down into simpler forms. Now, the more reactive of them will react with each other to form kerogen. During this process, some material is lost, given off in the form of various non-hydrocarbon gases. So kerogen is organic matter that has undergone some low-temperature alteration, or diagenesis, prior to the generation of oil or gas.
I mean, you think the kerogen would vary in different source rocks, depending upon the kind of living organisms you start out with?
Sure, they do. But we group them into 4 fundamental classes.
Under the microscope, kerogen appears as organic fragments that belong to different biological groups. Consequently, their chemical compositions also vary, and they will yield differing types and amounts of petroleum hydrocarbons. Type 1 kerogen is derived mostly from the remains of algae, either in marine environments or lakes. When it matures, it yields mostly crude oil. Type 2 kerogen consists mostly of amorphous particles, derived from the bacterial and mechanical breakdown of a mixture of marine, one-celled plants and animals. This kerogen is also oil-prone, but yields more natural gas than Type 1. Type 3 kerogen is derived from the higher land plants, the same types that form coals in swamps. Coaly kerogen yields mostly natural gas and has a rather low capacity to form oil. Type 4 kerogen consists mostly of inert particles that have been highly oxidized, like charcoal. It's extremely rare and has practically no ability to generate either oil or gas. Kerogen type is just one factor in determining if petroleum in the reservoir will be oil or natural gas. The burial depths and temperatures of the source rock is another. At very shallow burial depths and temperatures below about 60 degrees centigrade, some methane, called biogenic methane, can be generated by the initial bacterial breakdown of organic matter. However, significant petroleum generation does not begin until the source rocks become mature and are heated to about 60 degrees centigrade. At average subsurface temperatures, in areas that have a normal geothermal gradient, this usually occurs at burial depths of between 1 and 2 kilometers. At this stage, mostly crude oil is generated. The generation of increasingly lighter weight oils peaks at about 100 degrees centigrade and then declines slowly. At about 175 degrees, at depths normally between 3 and 4 kilometers, oil generation ceases, the oil window closes, and gas formation becomes dominant. When the formation temperature exceeds 225 degrees centigrade, kerogen usually has used up its petroleum generating capacity, and the source rocks become over-mature. However, methane can still be produced through the breakdown of the larger, heavier molecules of previously generated crude oil. Time can also play a major role in maturation. Young tertiary age rocks must be either deeply buried or have high geothermal gradients in order to generate significant amounts of petroleum. On the other hand, some older Paleozoic and Mesozoic source rocks may not have been buried very deeply, say only to the upper portion of the oil window. Yet there has been sufficient time for these rocks to generate petroleum. Comparing the role of temperature versus time, we feel that temperature is usually more significant.
So, do you see how this applies to the company's new well?
Well, the area is a delta, so most of the kerogen is probably type 3, since the rivers would bring in mostly land plants. And that would explain the high gas to oil ratio. But how would you apply the oil window concept here?
Pete, I think Dino wants to speak to you for a minute. I can answer this.
Good, because I don't think I can.
Of course you can. Now, the average worldwide geothermal gradient is 26 degrees centigrade per kilometer. Now, measured gradients range from lows of about 18 degrees to highs of 55 degrees. Now, deltas commonly have somewhat low geothermal gradients, so their production tends to be deep. Here, let me show you on this graph.
In areas that have relatively low geothermal gradients of 20 degrees centigrade per kilometer, source rocks will not become mature until buried to depths exceeding 2 kilometers. However, in this case, the oil window will be very broad, and some oil can still be generated at depths of even 7 kilometers. In contrast, a high geothermal gradient enhances the early formation of oil at relatively shallow burial depths, but it also causes the depth range of the oil window to be much narrower. The Earth's heat is also affected by the type of rock, that is, lithology, through which it flows, since rocks have different thermal conductivities. Thermal conductivity has an inverse relationship to the geothermal gradient. Some lithologies, such as salt, have very high thermal conductivities. This causes the geothermal gradient to decrease through an evaporite layer. In contrast, Coal and water-filled rocks with high porosity have low thermal conductivities, which cause the gradient to increase rapidly with depth. The geothermal gradient can be measured during drilling by making temperature log runs at various depths. However, this measurement covers only a moment in geologic time, the present. Since sedimentation and tectonic processes each create their own heat effects, it's logical to conclude that a sediment's temperature has fluctuated both up and down through geologic time. Paleothermometers, which measure the maximum temperature ever attained by a source rock at some time in the geologic past, are often a better gauge of maturation level of kerogen. There are many types of paleothermometers. Some measure kerogen properties that have been calibrated to temperature changes. The color of spores, which darken as they are heated, is one example of paleothermometer based on kerogen diagenesis. Vitrinite reflectance, or RM, which measures the shine of coal-like particles within the kerogen, is another. There are also various methods that relate clay mineral diagenesis to temperature. These diverse paleothermometers can be correlated to each other and to the temperatures of the oil and gas windows.
One of the engineers mentioned to me that you've been having some trouble controlling the pressure on this well.
Well, that's right, we have. Now, a lot of wells will encounter normal subsurface pressure, but here we've encountered an overpressured zone. That's not uncommon in a delta. We do have to avoid a blowout.
The total overburden pressure exerted at any point in the subsurface is the sum of two forces: the lithostatic pressure, or weight of the overlying rock, and the fluid or pore pressure. Normally, fluid pressure is the same as hydrostatic pressure, caused only by the weight of the overlying column of fluid. Now, this results from pore-to-pore communication extending up to the Earth's surface. The normal hydrostatic pressure gradients for a column of brine is about 0.465 psi per foot, or 0.107 kilograms per centimeter squared per meter. Both lithostatic and fluid pressure increase with depth, so the total overburden pressure also rises as burial increases. However, in a normally pressured well, the fluid pressure is always slightly less, and the lithostatic pressure slightly more than half of the total overburden pressure found at any depth. Now, this pattern doesn't hold for abnormally pressured rocks, which can be either underpressured if fluid pressures drop below normal, or can be overpressured as fluid pressure exceeds lithostatic pressure, which is more common. Overpressuring can develop whenever a permeability barrier, or seal, prevents water from being in communication with the surface. There are actually many ways to get overpressuring, but one of the most common ways, prevalent in deltas, is where sedimentation is too fast for deep shales to thoroughly compact and dewater. In this case, some of the weight of the overlying sediment, which is taken up by grain-to-grain contacts in normally compacted rocks, is taken up by the fluid in the pore spaces. As a result, the mineral grains within an overpressured rock may become slightly separated.
And such watery shales should have a low thermal conductivity.
Well, that's right. Now, they act as an insulating layer. They take up the heat, but they don't pass it on. Now, that's one reason why the geothermal gradients above this zone are low in a delta. Oh, excuse me, Paul, they need me up on the rig.
Well, that's okay. I'm going to check in with the drilling supervisor anyway.
Okay, listen, when you're through, why don't you come up on the platform?
All right, I'll see you in a few minutes.
How'd it go?
All right. I can see that maturation is a critical factor for source rock shales, but I'm not sure where rocks like the Green River oil shale fit in.
Well, let me see if I can explain. You see, oil shales are kerogen-rich rocks that haven't reached the thermal level needed to generate petroleum. Their hydrocarbons are still locked up in the kerogen and can only be produced by heating them to extremely high temperatures. It's a process known as pyrolysis.
Then, are the tar sands in Western Canada similar?
Well, now that's still open for debate. Some geologists feel that they are immature source rocks, like oil shales. But the majority feel that the tar sands are degraded oils, where flushing by fresh meteoric water and bacterial action have converted light oils into viscous asphaltic tar.
You wouldn't expect to find organic matter in sandstones, since it would probably stay in suspension, be windowed away during deposition.
That's right.
There are other reasons why organic matter is missing too, whether it's in sandstone or shales, and why not all shales make good source rocks. The recently deposited organic matter can be quickly destroyed by bacteria and animals that ingest sediment for food. Therefore, good source rocks usually have been deposited rapidly, as in this delta, or deposited in restricted, oxygen-poor waters. In either setting, the destruction of organic matter by living organisms is prevented.
I don't think I've ever understood how they got the oil out of the source rock and into the reservoir.
Well, I wish I had the answer to that one, too. You know, I still don't think there's any completely satisfactory solution to the problem of primary migration. However, from your perspective as an exploration geologist, it's probably not all that necessary to understand the details of migration out of the shale, as long as it's been established that there's enough source rock and that it's mature.
We do, however, have a good understanding of secondary migration processes, how the petroleum migrates to the reservoir once it has been expelled from the source rock. This can sometimes occur along an unconformity, along faults and fractures, or more commonly through an interfingering of source rocks with more permeable rocks.
Drill supervisor just told me the reservoir they're testing is sandstone. Now that's the most common type, right?
Well, yes, especially in the Delta province, but worldwide, carbonate reservoirs are almost as common as sandstone.
Yeah, and together they account for over 90% of the world's petroleum reserves. They're the only common lithologies that have the right combination of both porosity and permeability.
Porosity is a measure of the amount of void space in a rock, expressed as a percentage. But the only effective porosity into or out of which petroleum can flow is in pores that are connected with other pores. Isolated pores within a reservoir cannot yield hydrocarbons.
Aren't coarse-grained rocks, say, like sandstone, more porous than shales?
No, not at all. Porosity will be the same in two different rocks that have grains of the same shape and uniform sizes, even though their grain diameters may be different. But the permeability, the ability of a fluid to flow through a rock, will be affected.
Permeability decreases with finer grain sizes because the throat passages between grains and through which fluids flow are narrower and constricted. The measure of permeability is the darcy, or more commonly, 1/1000th of it, the millidarcy. Permeability in reservoir rocks commonly averages between 5 and 500 millidarcies, although some exceptional reservoirs have permeabilities up to 5 darcies or more. Gas may be able to flow from tight sands or dense limestones with permeabilities of only a few millidarcies or less. But oil, because it is more viscous, usually requires several tens of millidarcies to be commercial. Pore sorting will reduce both porosity and permeability because the finer particles both plug the pore spaces and create smaller pore throats. When a rock is buried, it compacts, and cement may infill the pores, reducing both permeability and porosity. When porosity is reduced below about 5%, most reservoirs are sub-commercial.
What's a good reservoir porosity anyway?
Well, most good porosity is between 10 and 20%, but a really excellent reservoir can have porosities of up to 30% more. However, the type of porosity and its continuity will differ quite a bit between carbonate reservoirs and sandstone reservoirs.
How do you mean?
Okay, let's go back to the mud house. We'll take a look at a thin section under the microscope. We got it from this reservoir here.
Sandstone reservoirs usually have primary porosity, formed when the sands were initially deposited. In sandstone, this porosity is usually intergranular, occurring between sand grains. Effective porosity is usually the same as total porosity. The continuity of reservoir quality in this case is mainly a function of the depositional environment and shape of the sandstone body. Newly deposited carbonate sands also may have primary intergranular porosity, and in some cases, fossiliferous limestones have original pore spaces preserved within skeletal grains, what we call intragranular porosity. However, limestones usually become cemented and recrystallized by diagenesis shortly after burial, and primary porosities are not commonly preserved. Most carbonate reservoirs have secondary porosity. This may be due to solution by circulating subsurface waters, which selectively dissolve out certain pore spaces, or to fracturing. The porosity may also be intercrystalline. That is, the rock is recrystallized and void spaces between crystal grains are created. Intercrystalline porosities are particularly important in dolomite reservoirs, as seen in this thin section. This texture is produced only in secondary dolomite, in which coarse crystalline dolomite has replaced calcite. A volume reduction of up to 13% accompanies this reaction and may help to create the secondary voids. In contrast, primary dolomite, which forms an association with evaporites, has porosity and permeability similar to other fine-grained lithologies, such as chalk and shale. It is usually porous, but lacks permeability, and thus has poor reservoir properties. The lateral continuity of carbonate reservoirs may be difficult to predict. Although primary porosity is closely related to depositional units, secondary porosity in carbonates, which is more common, often develops in an irregular manner.
Will you ever find secondary porosity in sandstone?
Oh, sure, it can create good reservoirs at depths where you'd normally expect sandstone to be tight. It generally involves the leaching of carbonate cements and grains, or unstable minerals like feldspar. Secondary sandstone porosities are common along unconformity surfaces, and they can provide important pathways for secondary migration.
90% of the world reserves are in sandstone and carbonate. What about the rest?
Well, you'll find them mainly in certain fractured reservoirs, and fracturing can be found in any brittle lithology. Want some coffee?
No, thanks.
Although in some cases, sandstone and carbonate reservoirs owe some or all of their porosity and permeability to fracturing. It can also be found in lithologies that are not normally reservoirs, such as shale and even metamorphic and igneous rock.
I've always wondered how thick a reservoir has to be in order to be commercial.
Well, the gross pay, that's the total vertical reservoir internal, can range from only a meter or two to several hundred meters in places like the Middle East and the North Sea. Of course, not all of the gross pay interval is necessarily productive. It could be shale stringers or well-cemented horizons that contribute to the gross pay, but not to the net pay. Net pay refers only to the productive reservoir.
Well, Peter, sorry to interrupt, but we need you out on the rig.
Okay.
See you in a little bit? Or why don't you come along? Sure. All right, I'll see you over there. Okay. What kind of trap have you found here?
Well, in this case, it's called a rollover anticline. It's only one of a number of ways in which oil and gas can be trapped. Let's go catch up.
Okay.
A trap may contain oil, natural gas, or a combination of both, with gas, being lighter, trapped at the highest level. Beneath the oil and gas columns, the pores of the reservoir rock are filled with water, which is, with few exceptions, heavier than the oil. The planar boundary which separates these two zones is called the oil-water contact. It marks the deepest level of producible oil. Water in the pore spaces of reservoirs can exist in two forms, as free water and as more tightly bound interstitial water, absorbed onto the surfaces of mineral grains. In permeable rocks, most water is free water, and this is the water that becomes displaced when petroleum enters the pore spaces. But the interstitial water, although it will never be produced, is present even in petroleum-filled reservoirs. Usually, the oil-water contacts of reservoirs are sharp. However, in less permeable, finer-grained rocks, where the interstitial water becomes more prevalent, fluid contacts are more gradational. The gas-oil contact, or gas-water contact, if no crude is present, can be described in a similar manner. The distance between the highest and lowest point of the trap is its vertical closure. In the case shown here, the trap is filled to its lowest point, the spill point. Frequently, however, traps are not completely filled, and the oil-water contact is higher than the spill point. Most traps fall into one of three categories. They are either structural traps, stratigraphic traps, or traps that combine both structural and stratigraphic aspects. Anticline folds, such as we see here, are the most common type of structural trap, and these can originate in many ways. Deformation by compression can produce anticlinal traps. Now, these can occur either alone or in combination with reverse and thrust faults. Areas of extension and normal faulting develop compactional or drape anticlines, which form traps over basement-high blocks or some other rigid feature, like a reef. Sediments draped over an underlying structural high are thin when compared to adjacent low areas. As they're buried, the sediments in both regions compact, but the thicker sediments over the low areas will undergo greater compaction. This produces an anticlinal closure, which may be enhanced still further by deep-seated recurrent fault movements. Drape anticlines are formed when deformation occurs at the same time or shortly after deposition. And that's also true of rollover structure. In deltas, where thick, heavy sands are rapidly deposited over less dense, unconsolidated clays, a type of fault called a growth fault is generated, which remains active as sedimentation continues. Equivalent stratigraphic sequences are much thicker, down-thrown to the growth fault, and sediment slumps toward the fault plane, creating a structure called a rollover anticline. Diapirs, caused by the upward movement of low-density material, usually salt or in rare cases clay, can generate anticlinal traps in the overlying strata. Stratigraphic traps, caused by the pinching out of permeable lithologies, can develop along the flanks. In some cases, the salt diapirs will actually pierce through the sediment layers. And this will produce even more trap types due to truncation and faulting.
Sounds like faults are associated with folds.
Now, most anticlinal traps have some faulting associated with them, but these faults don't always play a role in the trap.
And faults can be traps in their own right, too. In either case, the fault planes must be tight and impermeable in order to get accumulations of petroleum. Even though the faults may be mapped seismically, there is often no way of telling whether a particular fault is impermeable until a test well has been drilled.
Now, seals. While an anticlinal trap usually requires just an impermeable cap rock, fault traps must be tight, and they must be sealed by impermeable lithologies, both vertically and horizontally.
That's generally by a shale or evaporite, right?
Right, or any dense impermeable rock like a carbonate or a tight sandstone. Now, there are even a few small fields where leaky fault traps are capped by their own degraded asphalt, which acts as an impermeable barrier to further leakage.
Isn't there a field on the western part of the states where there's a fault trap sealed by overthrusted granite?
But that's very, very rare. There are all different kinds of traps. Why don't we take a look at some of them?
Stratigraphic traps are due to lithologic changes, and they fall within a wide range of categories. Some stratigraphic traps are associated with unconformities. They may occur below an unconformity. For example, a tilted and truncated sandstone reservoir can be sealed by a post-unconformity shale. They may also occur above the unconformity. Unlap traps occur when a sand pinches out against a topographic high on the unconformity surface. And topographic lows may be filled with channel sands with good reservoir properties. Channels may also occur within normal conformable sequences. Depending on the depositional environment, traps can form in river channels, distributory channels of a delta, and submarine fan channels of deep basin sequences. The sands that fill the channels usually interfinger or are otherwise surrounded by muddy deposits, which often become both source rock and impermeable seal upon burial.
I think that some sandstone bodies would be long, narrow, meandering rock bodies whose trends would be hard to predict.
Well, there are some twisty things, but their distribution and patterns are not completely random. With some care and a certain measure of luck, we can determine both their trends and their patterns. Okay, now there are some other traps we should consider.
Coastal barrier islands and bars can also form stratigraphic traps when they interfinger both with shallow lagoonal and deeper offshore muds. Although, like channels, they form elongated, narrow sandstone bodies, barrier sands are often larger and straighter. Consequently, they generally produce larger individual reservoirs than channels, and because they follow ancient shorelines, their trends are easier to predict. Carbonate reefs can be a very important kind of stratigraphic trap. They form in tropical, shallow seas, often where nutrients are upwelling from adjacent, organic-rich, deep-water, muddy basins. They are initially deposited as skeletal networks with a very high porosity, which to varying degrees may be preserved upon burial. However, much of the porosity of reefs is secondary and hard to predict. If a high porosity and permeability is preserved, reefs can form really large traps, since they usually lie adjacent to thick basinal source rocks. Reef traps can have various geometries. They can be individual isolated bodies, like the Intersar reefs of Libya. Some are elongated barrier reefs, like the Golden Lane of Mexico. And they can be circular, like the Horseshoe Atoll of West Texas. Another type of stratigraphic trap may be formed through diagenesis. Diagenetic traps are caused by differential cementation or solution. They're not a very important trap type by themselves, but diagenetic effects are often associated with some of the structural and stratigraphic traps we've already discussed. That brings us to combination traps, which are due to two or more of these different trapping mechanisms acting together. There are many ways in which different trap types can combine, but some sort of structural stratigraphic trap is the most common. Here, for example, we see fault unconformity traps, in which tilted fault blocks are truncated and overlain by post-unconformity shale.
Now, fluid flow will also act in combination with structural and stratigraphic aspects to create what we call a hydrodynamic trap, but these are extremely rare.
How common are the different kinds of traps?
If you consider only giant oil fields, namely those that contain over 500 million barrels of recoverable oil reserves, or 3.5 trillion cubic feet of gas, about 75% is in anticlines, 13% in stratigraphic traps, 9% of the oil is in combination traps, 2% in traps caused by salt diapirs, and 1% in fault traps. Although stratigraphic traps are less common than structural traps, they're becoming increasingly important. They've been difficult to find because subtle lithologic changes don't show up well seismically. But now enhanced seismic techniques are becoming available, which should improve our track record with stratigraphic traps.
Seismic techniques are the most sophisticated way to locate new fields because there aren't too many surface detectable anticlines left that haven't already been tested.
Surface shows such as seepages, oil slicks, gas detection, and water wells can often indicate the petroleum potential of a sedimentary basin, but it isn't very useful in deciding where to drill.
Yeah, but are surface seeps a new exploration technique for new unexplored basins?
Well, yes, they can be useful, but fundamentally you have to look at the total picture.
Yeah, what we look for is the right combination of organic source, rocks, reservoir structures, and geothermal history.
The age of the basin is important, too. About 40% of the world's reserves come from young tertiary-age rock, about 50% from Mesozoic rock, and only 10% from old Paleozoic strata. So young, often small basins along active continental margins frequently yield considerable petroleum. They may be undergoing deformation and are often geothermally hot. But old, large basins in the stable interiors of continents are generally less petroleum-rich provinces. There are some good ones around, but many of these make poorer prospects.
So it isn't just the bigger the basin, the more oil. So how do you decide what's the best area to drill?
Well, that depends on the basin type. There are 10 fundamentally different types of petroleum basins.
Now, that number can vary depending on the classification scheme that you use. But geologists do agree that basins have different petroleum habitats that can be correlated to the broad aspects of their geographic setting and deformation style.
Some basins are characteristic of the stable interiors of continents, or craton, and they generally have a simple convex geometry. Some have a single depositional cycle. Others have had sedimentation interrupted by uplift and deformation processes, and this is reflected in a major unconformity which divides the sedimentary sequence.
Basins may also develop along passive continental margins, where continents have been broken apart. These develop as thick prograding sediment wedges with a one-sided source on the continents. But they usually start out as rift basins, where vertical horst and graben faulting play a major role in basin development. Active continental margins, characterized by compression at the boundary between continents and oceans, can also lead to several basin types. These are found either in areas where ocean trenches and volcanic island arcs develop, where deformation relates to long, laterally moving faults, or within young mountain belts created along the edges or interiors of continents.
And then there are the deltas, which are a kind of basin that is a later overprint of many of the other basin types.
Now, because of past exploration efforts in basins worldwide, you can make generalizations about the habitat of oil and gas in specific basin types, and then make predictions that'll be useful in future exploration.
Well, in that case, what's your prediction for this delta?
Well, good quality reservoirs in delta front sand, deep production because of the young age and low thermal gradient. What do you think, Pete?
Well, I'd say a number of moderate individual-sized traps and growth faults, rollover anticlines, and maybe traps associated with dye piers, paraffinic oil, but also good gas enrichments.
In short, there are probably no giants out here, but there should be a good number of moderate-sized commercial prospects.
And your job,
guess what,
is to find them.
I'll give it a shot.
Okay, well, we go to dinner.
I'll join you.
No, you find one and then you
wait
can
a minute.
Just a little one. You just got to find a little one.
It doesn't have to be
and
a
then
big
you can
one,
eat.
a giant one.
Each video module consists of a video program presenting an overview of the topic and a manual containing much more detailed information as well as exercises. To master each topic, you must use the module's components together. View the video program, read the manual, and work the exercises.
After this module, we start to specialize. Each later module addresses one specific aspect of the fieldwork or the processing or the interpretation. This is the last chance we get to take the grand view. And the grand view is important, the overall vision of the place of geophysics in the whole scheme of exploration. Let me say it out straight. Of course you want to advance your career by becoming an expert in some specialization of geophysics. But your career will advance further if you also have the grand view. And it will be much more interesting, too. So let's look in more detail at that important middle ground between geology and geophysics. Let's talk first about structure, the traditional service of geophysics to geology.
To the geophysicist concerned with structure, the nature of the Earth is described by two quantities: velocity, because velocity defines the ray paths and the reflection times, and acoustic impedance, because that defines the reflection amplitudes. So velocity, then, and density.
Next, we recall from GP 203 that for a given series of layers of given thickness, we can use the known velocities and densities to obtain the reflectivity series. On each spike of this series, we can erect the appropriately scaled reflection pulse and add them all together to obtain the synthetic seismogram.
Which can be on a scale of reflection time, of course, since we know the layer velocities.
Right. So from a model of a set of flat-lying layers, we can compute the corresponding seismic reflection trace.
Next, we recall that if the layers are not flat, we can construct normal incidence rays from each surface point to each reflector, and so compute the reflection response at that point. Then a number of such surface points gives us the whole seismic section.
And this simple use of rays is sufficient to alert us to a situation where several normal incidence rays are possible, so that the seismic section must not be taken at its face value.
Next, we recall that for the full picture, we must abandon the simplicity of rays and use waves. However, it's still not too bad. On every interface, we regard each point as a Huygens source, sending out its spherical wavelet back to the surface,
where it generates across the corresponding traces a pattern that we call the Huygens hyperbola, or the diffraction hyperbola.
Then we do the same for all the other points on the interface, obtain the corresponding Huygens hyperbola for each one, and add them together.
For example, if this is the depth model, with the velocity and density known for each layer, then by adding all those hyperbolas, we get something like this, the corresponding time section.
Given enough computer power, we can extend the technique to 3 dimensions and incorporate real-world nasties like transitional reflectors and lateral variations of velocity within layers.
In fact, we can construct the near-trace seismic section for almost any Earth model, using just the velocity and the density in each layer. That's all we need for the near-trace section, involving reflection only at normal incidence. But if what we want is to construct stacked sections, where the long offset traces in each gather represent wide angles of incidence, we remember that we also need some sideways property of the rocks, either the shear velocity or Poisson's ratio.
Finally, if the reflection pulse in our synthesized sections is to show a real-world broadening with time, we must include the absorption measured either as dB per wavelength or as Q.
So, simplifying all that somewhat, we have just 4 variables: density, the 2 velocities, and Q, totally defining the Earth as the geophysicist sees it.
All this is very comforting. Given almost any set of rock layers and these 4 variables for each, we can synthesize the full stacked seismic section that we would expect to get from it. This is good. It helps us to understand why in complex zones some interfaces show and some are hidden. It helps us to design the field techniques. It helps us to check an interpretation by modeling it back to a synthetic section and comparing that with the real section. What is more, this checking concept can be made interactive. Either at the scale of a single trace or on a piece of section, we first set up some reasonable model of the Earth as we think it might be. Then we construct the synthetic and compare it with the real, deriving some number saying how well it matches. Next, we make some plausible change to the model, reconstruct the synthetic, and ask, is the match better or worse? That tells us in which direction to make the next change. Again, we reconstruct the synthetic and ask, is the match better or worse? And so on, gradually homing in on an interpretation that best fits the real data. We should not get too excited about this. The details are tricky, and the answer is neither unique nor necessarily the best. But it does illustrate that the seismic description of the Earth is a nice, tight little system. Given any configuration of layers, we need just 4 variables in each layer, and the Earth is specified in seismic terms. The layer thicknesses may vary, of course, and the 4 variables may vary within each layer. But we don't need more than just the 4 variables. We can forward model the seismic response to this Earth with confidence, and we can home in on a satisfactory match between this model and the actual observed response. Yes, it's a nice, tight little system. The problem, of course, is that our 4 variables, VP, rho, VS, and Q, are not the ones wanted by the petroleum geologist. This is where the trouble starts.
We've looked at the geologist's wish list before. Here, we just pull out of it a few of the really critical variables.
Well, it's tough, but it's not impossible. Structure, of course, is what seismics does best, provided that the interface in which the geologist is interested does generate a reflection or is conformable with one that does. We can generally map structure with confidence.
In time.
In time, and nowadays, better and better, in depth. So I'm going to say yes to structure.
Okay, now let's look at the tectonic and burial history. We remember the technique from one example of salt pillowing that we worked in GP 501. We mark the major unconformities and the other major picks, noting their message of layer thinning and thickening. Then we remember we strip off the first layer by bringing its base up to the surface, and so on with each layer in turn, each such operation moving back one stage in the tectonic history, so that finally we see how it all happened.
From such a tectonic history, we can infer the maximum depth of burial of particular rock units and how long they were there. Using this example in GP 501, we constructed 6 prior stages of the tectonic history. And back slowly to today. We see, of course, that the older layers are going deeper, and we now want to put this process on a time scale. Let's consider one location along this profile, say here in the trough, and go back all the way to the beginning of Zechstein deposition in the Permian.
And what we're after is a plot relating depth to geologic time, in terms of the succession Permian, Triassic, Jurassic, Cretaceous, Tertiary, or in equivalent terms of millions of years before the present.
Right. Obviously, at the beginning of Zechstein time, the base Zechstein was at the surface, depth 0. While at the end of Zechstein time, the base Zechstein was at this depth. So the base Zechstein went down more or less so.
The end of the Zechstein here is the start of Triassic, initially at 0 depth. At the end of Triassic time, the base Triassic was at this depth, going down more or less so, with the base Zechstein going on down below it.
Top Triassic is base Jurassic, which goes on down for a time, with the others below it. Very likely there was more Jurassic, and everything went down some more, but we cannot know for sure because of the unconformity. Obviously, after the Jurassic went on down, it was uplifted again, and much of it was eroded off.
So we cannot pick up the story again until the Upper Cretaceous. By the end of the Upper Cretaceous, the base is down to here, and the others appropriately deeper.
And so on. By this time, in the Tertiary, we have the base Tertiary down to here, and the others appropriately deeper.
But later in the Tertiary, when everything is down to here, we meet another unconformity, largely a consequence of the accelerated salt movement. So another gap in our plot.
And finally, we come to the present, when after some more deposition, everything is down to here. At this particular location along the line, we have a plot of the burial history of each layer, depth as a function of time.
Of course, there are some details we must attend to. Our original reflection times must be converted to depths, And we need to crank in some reasonable degree of compaction, appropriate to each rock type. A lot for the shales, less for the others. But the key question, obviously, is what we do about the gaps.
Well, from the rest of the line and from other lines, we can usually get some idea of how much further down the succession went and how much further up it was uplifted. So we can make an informed guess.
And then we have a valuable display. We can superimpose on it the local kitchen conditions that favor the generation of oil and the generation of gas.
So that if in this area there are potential source rocks in the lower Jurassic, we can see that these rocks have been in the oil window for about the last 35 million years, and perhaps for 10 or 20 million back in the upper Jurassic. We have some chance of oil from these source rocks, no chance of gas.
That's right. If we are interested in gas sourcing, we must go back into the pre-Permian.
So going back to the geologist's wish list, under reasonably favorable circumstances, I'm going to say yes to tectonic and burial history.
And half a yes, perhaps, to saturant. Not in the sense that we know that hydrocarbons are present, but in the sense that if they are present, we have a lead as to whether to expect oil or gas.
Let's look next at rock type. We have several approaches. Right now, let's concentrate on the one that infers rock type from depositional environment, in the sense that, dune sandstones form on arid land, limestones are profuse in warm, clear, shallow water, shales in the deeper offshore, sandstone bars in the near offshore.
We have seen many examples in the manual of GP 501. A wedge of sediment thinning by sediment starvation, any sandstones present being likely to the right, silts and clays to the left, a pod of sediments from a local sediment source, deposited from its confused internal structure under high energy conditions, except at its toe, a fan of sediment formed against a fault scarp, again with the coarsest grain material expected closest to the source, the typical pattern of marine onlap in a period of rising relative sea level and with good sands likely close to shore, an erosional channel with potential for high-energy clastic infill, and so on.
So we ask, can we formalize the recognition of depositional environment, and from that our expectations of rock type?
Let's start with a very simple example. On the flank of a basin, perhaps a simple pattern like this.
Well now, who remembers the infamous Chapter 10 of GP 203? This is what we do.
First, we pick the unconformities, recognizing them, in this case very simply, by the angular truncations. We remember not to be fazed by the occasional changes of amplitude, or even of polarity.
Okay, then these two unconformities become sequence boundaries. They divide the reflections into 3 zones, each of which has a distinct reflection pattern, representing a distinct genetic unit.
We remember also that reflections from within each such unit are generally stratal reflections from bedding planes.
And that even in zones where an unconformity itself may generate no reflection, the unconformity is revealed by the termination of stratal reflections.
Okay, now let's take the message about relative sea level. Where was sea level at the time this unconformity was being eroded?
Well, somewhere off to the right, relatively, very low.
And where was it later, when these sediments were being deposited?
Well, somewhere up there, relatively very high.
And later, when these sediments were being deposited?
Down there, relatively low again.
So when we see a pattern like this, we infer a cycle of relative sea level, from low to high to low again, and with the 2 sequence boundaries representing the times of low stand.
So let's graph it, relative sea level against time. Here we say low relative sea level at this time, then a rise through this value at this time, a turnover and down to this low stand at this time, followed by a rise through this value here. One sequence cycle of relative sea level.
So cycles of relative sea level obtained from seismic data.
Yes. Now let's ask what is happening to the coastline during these ups and downs of relative sea level.
The key is to look for the break in slope. At the time this interface formed, the actual situation was like so. Then the break in slope is the depositional coastal break. which commonly occurs at a water depth of about 10 meters.
So we know in what water depth the sediments were deposited. Landward of the break above Fairweather wave base. Seaward of it below wave base.
Here, shallow water sediments deposited under high energy conditions. If there are coarse-grained sediments available, this is where they will be.
Here, deeper water sediments deposited under calmer conditions. Very likely fine-grained sediments, quite uniform.
And the coastline itself is typically several hundred meters landward of the coastal break, which marks the boundary, of course, between the shallow water deposits of the marine margin and the non-marine deposits of the coastal and alluvial plains.
So, going back to the present picture, we see that the movement of the depositional coastal break gives us the likely movement of the coastline, and thus the movement of coastal rock types.
Obviously, this is very important. From the seismic reflection pattern, we track the depositional coastal break, and hence the coastline. Then we know the depositional environment here, fluvial deposition on the coastal plain, and here, tidal flats, and here, a high-energy shallow water environment, yielding to this low-energy fine-grained deposition in deeper water.
And from the depositional environment, we can guess the rock types. Given suitable sediment supply, we expect generally undifferentiated non-marine sediments here. A good chance of sorted sandstones here, and marine shales out here, with, of course, a transitional tidal zone here and another transition here.
Okay, rock types from seismic reflection patterns. Let's take a more complex example.
Well, as we did before, let's start by recognizing the sequence boundaries. I see clear angular relations here, on-lap, and on-lap, and down-lap, on-lap again, and down-lap. Tracing through such points, we have a lower sequence boundary, an erosional unconformity down to here and uneroded thereafter, and an upper sequence boundary, the same. So for simplicity, let's restrict ourselves to the one sequence between these sequence boundaries. Okay, that's better. Now, let's trace the movement of the depositional coastal break starting here, the lowest place we see it, and going up and out, like so.
This outbuilding, or progradation, is telling us that the volume of arriving sediments is greater than the space made available by the rise of relative sea level. But after this, we see a dramatic change. There is retrogradation of the depositional coastal break, telling us that the relative sea level is rising faster than the sediment supply.
Then, after that, the relative sea level is again unable to keep up with the sediment supply, and we have a major outbuilding.
So that in the simple case of constant sediment supply, we have this message. During the deposition of this sequence, relative sea level rose from here to here, initially slowly, then rather fast, and then progressively more slowly again.
Of course, there's a lot more on this message in the manual, but here, let's be sure to take the inferences about depositional environment and rock type.
Okay. In this illustration, the extreme low of relative sea level occurred here, accounting for the eroded nature of this sequence boundary, including the eroded valley here. At that time, the surface of the solid Earth looked like this. In fact, let's start our visualizations just a little before this, when the relative sea level was still falling, and not yet so much erosion. Then the full picture might well have been like this.
On a scale of 1 to 10, let's say this is relative sea level 5.
We see the high ground far above sea level, yielding to lesser gradients, where the streams are braided but fairly straight. Then the alluvial and coastal plains, where the rivers meander. Then we see the deltas, outbuilding their sediment fans into fairly shallow water.
But if the relative sea level falls any further, any coarse-grained sediments in those deltaic fans will themselves be eroded and be transported down the slope. So if we visualize such a fall, say to level 4, the first thing we expect to see is a basin floor fan.
Which makes our eyes light up, because basin floor fans often make excellent reservoirs.
Okay. Now, the erosion continues while the relative sea level stays low. The eroded valley we saw in our original cross-section is now well developed. The big canyon deepens, and the products of the erosion begin to fill in the slope to form a slope front fan.
Generally of mixed sediment. Some coarse-grained materials, especially associated with those channels we see, but not showing the excellent sorting that is characteristic of the basin floor fan below it.
Now the relative sea level just begins to rise towards level 5. A rising sea level makes more space available for sediments in the valleys and close inshore. We have a low-stand wedge of sediments. The delta, coupled with the winnowing action of the waves, offers scope for sorting and cleaning of the coarse-grained sediments. And the rising relative sea level acts to preserve any such bodies of coarse-grained sediment.
Now comes the fast rise, way up to level 8. This makes available far more space than the sediment supply is able to fill. So we get a major transgressive system with thick non-marine sediments backed up on the coastal plain, and starvation of fine-grained sediments out to sea.
So here we have generally poorly sorted sediments, except where sorting is achieved by the rivers, such as in point bar situations. The greatest scope for sorting occurs from waves at the shore face. Again, any sorted coarse-grained deposits are rapidly buried and preserved by the rising relative sea level.
Now the rate of rise decreases. The sediments can more than fill the additional space, and so the coastline regresses seaward again.
For the first time, we now have alluvial deposits here, distinct from those of the coastal plain, a high-stand system.
While we have that on the screen, let's just take note of this surface. It represents the surface of the solid earth at the time of maximum landward movement of the coastline. It is the maximum flooding surface that we looked at briefly in the GP 203 manual. It looks like an unconformity, but without erosion. It is not a sequence boundary.
No. To get another sequence boundary, we need another cycle of relative sea level. That would ordinarily start with another fall, which would erode the top off these existing sediments. But just for interest, let's say that there is scarcely any fall, just a still stand, before the relative sea level rises again. Then what we can expect, as the rise starts again, is this: little or no upbuilding. Indeed, until the rise starts in earnest, there may even be some erosion of the coastal plain. All the sediment is bulldozed over the edge to form new shelf margin deposits. And this becomes the second sequence boundary, signaling the end of the first cycle of relative sea level and the beginning of the next.
Okay, between the two sequence boundaries, then, we have our original reflection pattern. But now, in our mind's eye, we see the whole train of geological events that gave rise to it. This visualization tells us the depositional environment of every piece of rock anywhere in the pattern. And so, depending on the sediment supply, the type of rock that we can expect anywhere in the pattern.
Stress that proviso.
Yes, of course. A marginal marine environment can give us coarse-grained sandstones only if the sediment supply includes coarse grains. It's a lead, not a promise. But still a reasonably good lead if we can see that the sediments are derived, say, from a large basement uplift off to the left.
Okay, so we see the scheme. We identify the sequence boundaries, each corresponding to a relative low in sea level. Track the movement of the depositional coastal break and the coastline as the relative sea level rises, and infer what kind of sediments, what rock type, is likely to be deposited where. Let's illustrate it down here.
At the beginning of the sequence, with relative sea level at a low, we hope to see the basin floor fan in this position. Often an excellent reservoir sandstone. A prime target.
Next, we remember, comes the slope front fan, generally of mixed sand silt clay composition, but with a potential for good sand accumulations in the channels, and possibly in overbank splays. So occasionally, good reservoir sandstones, but difficult to find.
Then comes the low stand wedge. Here, there's the possibility of infilling previously eroded channels, sometimes with coarse-grained sediments. But again, those things are difficult to find unless they're large. Then there is potential in the sands of the coastal belt. Landward of those are non-marine deposits of mixed composition, generally dull, but occasionally relieved by sand-filled river channels, point bars, or extensive sand dunes. While seaward of the coastal plain, of course, we expect only marine shales, potential source rocks, perhaps, but of no interest as reservoirs.
Except that at the bottom of every slope, there is always the potential of sorting by sliding and the formation of shingled sands at the toe.
Which would take some courage to drill in that position.
Well, yes, but remember we can still do this type of analysis after the whole region has been folded and faulted by taking out the structure and unfaulting the faults. Any of these sandstone bodies may later be structurally high and a good target.
Well, that's true. Now, while we have the low stand wedge in our sights, let's just look at the detail of this potential sandstone body. First, our tracking of the depositional coastal break tells us where to drill for the greatest thickness of sandstone. Second, we can ask what is the message of reflections, such as these, within the low stand wedge.
Well, in GP203, we talked of those as parasequence boundaries. Parasequence boundaries caused by higher frequency cycles of relative sea level superimposed on the general rise between sequence boundaries.
Right. So let's look more closely and ask why we've done this.
Well, that cannot be right. For a start, the transition from sandstone to shale is gradual, not abrupt as you have shown here.
Yes, of course. This is just for diagrammatic purposes, to show more clearly the curve here and the reversals shown as coincident with the parasequence reflections.
Yes, I was just asking myself why those would be coincident.
Well, first, the very presence of those reflections within the wedge tells us that there were higher frequency cycles of relative sea level superimposed on the general rise.
Right. No such cycles, no such reflections.
Next, according to GP203, many or most stratal reflections are born at accelerations and decelerations of relative sea level. So, looking at these two reflections in particular, we can visualize relative sea level doing this: a general slow rise with a higher frequency small amplitude cycle superimposed on it, so that the velocity of sea level rise is like so, and the acceleration is like so.
Oops, that acceleration is the wrong polarity.
No, you're thinking in terms of reflection time, increasing downwards. This is differentiation against geologic time, increasing upwards.
Ah, yes, okay.
Now, each reflection that we see is therefore a doublet, composed in many cases of an initial negative reflection interfering with a later positive reflection.
I'm going to have to read the infamous Chapter 10 again. It seems to me that sometimes a thin limestone might form in there on the shelf, in which case it would start positive and be more complicated.
Of course, we're talking only the coarsest generalizations here, and one particular type of shelf sequence. The details are subject to all manner of changes, dependent on local conditions. But let's press on to the next system, the big transgression, as the relative sea level rises rapidly.
Those new gray rocks are almost certainly shales, of course, which is good for sealing those reservoirs in the low stand wedge.
We don't have to go through the rest in detail. We can see generally, by tracking the coastal break, where the largely undifferentiated non-marine sediments are likely to be, where the marginal marine sandstones are likely to be, and where the shales are likely to be, together with all the lateral transitions between these rock types.
With fair potential for reservoirs in the marginal marine sandstones, provided that we can find a seal.
And particular potential at the zone of maximum flooding, because of the stacking of so many sandstone bodies, all testable with a single well.
Okay, let's go back to our wish list. Dare we check depositional environment?
Well, what we've been doing needs good seismic. It needs lots of seismic over at least one flank of the basin. And let's face it, sometimes the unraveling is tough. But yes, we have the tool, and we begin to make great strides.
And where we can get the depositional environment, then we have a good lead on the rock type. Not always, because it must depend on the sediment supply, but often.
Okay, so now let's ask about geologic age.
Well, what age markers could we possibly hope to identify in a seismic section? Answer: the major unconformities. For although local unconformities may be formed by local causes, by local uplift, for example, with no useful inferences about sea level, a major regional unconformity generally represents a major low stand of global sea level.
For example, suppose we see this section. We quickly identify the sequence boundaries. Then we look for evidences of where sea level was at various times. We look for evidence of coastal onlap. The earliest evidence is here. Then we see the coastal onlap rising up the eroded unconformity surface, all the way to here.
The next evidence of coastal onlap is way down here, so relative sea level must have fallen, like so. We can estimate the amount of that fall. The fall in the position of coastal onlap as so many milliseconds, and hence as so many meters or feet. Let's suppose that in this case the answer is 350 meters. Then we know immediately from the magnitude of the fall that we are looking at a major global event. There are not many falls of 350 meters in geological history.
To find out which one it is, we graph our conclusions about the position of coastal onlap. First, we have the rise, from here to, at least, here, which we may plot like so. In fact, that's not quite right, because ordinarily this point out in the basin would have subsided more than this point. We can get some protection against differential subsidence by measuring the rise in a series of steps up the unconformity. First, a vertical rise. Then, because a stratal reflection is a surface of constant geological time, the next measure of the rise. Constant time again, and the next part of the rise. Constant time again, and the last part. The total rise, then, adds up to rather less than before.
Okay, then we have the fall, from at least here to here. We may plot it like so, 350 meters, the rise and the fall.
We can continue in the same way. From this low, the coastal onlap rises at least to here, rises to here, and so on. A fall to here, a rise, a fall, a rise, outbuilding to a still stand, and so on. The coastal onlap chart.
At this stage, the scale for the level of coastal onlap is calibrated, in meters or feet. But for the other scale, which is just a succession of events in geologic time, we have as yet no calibration.
Let's concentrate first on the rises. Then some help comes from looking at the volumes of sediments between events. During the first rise, a large volume of sediments. During the next rise, a small volume. So if the sediment supply is more or less constant, these volumes give some idea of the duration of each rise. And we can adjust the rise times on the onlap chart accordingly.
About the duration of the falls, however, this type of analysis may yield little, because the evidence is usually eroded. So with no evidence at this stage, we'll admit we don't know and concentrate on the rises. Now this obvious stillstand reminds us that some degree of stillstand must be normal before a fall. So this is a more usual appearance. We see then the typical appearance of a coastal onlap chart, except that we usually turn it to make the time axis vertical. Now, the key step. We can also do all this in an area where we have abundant well control, where we know the geologic age of each sequence. Indeed, we can do it in many such areas all over the world. From these, we can establish a master chart of relative coastal onlap, high, low, as a function of geologic age, on a scale of millions of years. Now, if we look at our chart, in comparison to the master chart, we can see that there is a local character match here. At the same scale, we see that the match is not perfect.
We would scarcely expect it to be perfect, what with variations in local sediment supply and erosion, and local variations of subsidence.
But it is enough to give us a good lead. If the same message is borne out on other lines, we grow increasingly confident that these sequences fit on the geologic timescale here. So that this big fall occurred about 60 million years ago, and so that we can date this unconformity at about 60 million years.
Very good. That's a bonus we did not expect to get from seismic data.
Indeed. So let's go back to our wish list and put a qualified yes by geologic age. It has to be qualified because there are pitfalls and doubts along the way, which we shall talk about in later modules. but nevertheless a yes.
Fine. Now let's look at what's left on the wish list. Let's see if we can add to the specification of rock type and do something about these.
For which we must return to a matter we broached in GP 202. What is the relation between a rock as a geologist sees it, for example in thin section, and a rock as we see it, that is, as a substance having a density, a compressional velocity, a shear velocity, and a Q?
The density, as we have agreed before, is easy. However many components the rock has, coarse grains, cement, fines, water, oil, the rock density is always the sum of the component masses divided by the sum of the component volumes. And in practice, since the densities of the grains and the cement and the fines are all much the same, the decisive factor is the porosity. Density goes, first and foremost, with porosity.
But velocity, we remember, is not so simple. Let's start, for a change, with shear velocity, V sub s. Any velocity, we know, is always the square root of the appropriate elasticity over the density. And for shear, the appropriate elasticity, stress over strain, is the rigidity, the reluctance to change shape. So shear velocity, V sub s, is the square root of the rigidity over the density.
Now, moving towards real rocks, our first step, as before, is the cubic packing of spheres. When we shear, each sphere changes shape, but not volume. Provided there is overburden pressure, the grain contacts do not slip. If we imagine lines drawn through the grain between opposite contacts, we see what happens. The inner part of the grain just rotates, while almost all of the shearing occurs in the outer shell, near the grain contacts.
So the rigidity, and hence the shear velocity, depends on the way that the cross-section of the grain thins as it approaches the contact. Thus, this mythical but very angular grain would have small rigidity. The contact zone would bend very readily and allow the central zone just to rotate, whereas the sphere is less bendy near the contact. Greater rigidity, higher shear velocity.
But there's a change of porosity also between those two.
Yes, but it is not the change of porosity as such that is changing the shear velocity. A grain like this, fanciful though it may be, illustrates the point. It has the same porosity as the sphere, but lots of give in the contacts. Small rigidity, low shear velocity.
So with more realistic grain contacts, a lot depends on how the grains thin as they approach the contact. We must brace ourselves for some dependence of shear velocity on the angularity of the grains.
Except that this dependence can be lessened by modifications to the contact. For example, at shallow depth, an angular contact may look like this, being very bendy near the contact. At greater depth, with the contact compressed, the flexibility is much reduced. The shear velocity increases with compaction. Cement has a large effect at shallow depth, but less at great depth. And if the compaction is sufficient to cause solution and recrystallization at the contacts, then the original flexibility is very much reduced.
And opposite effects. Here's a rounded contact at average depth. Not much flexibility in that flattened contact. But the same contact in the presence of overpressure becomes more bendy, reduced shear velocity.
Let's see what else affects shear velocity. Well, the number of contacts per grain, that's important too. If we hold the grain in place at more points, resisting deformation, the rigidity increases, and the shear velocity with it. So if we go from this cubic packing of spheres to this more efficient packing, the shear velocity increases. Not because the porosity has decreased, but because there are now 12 contacts per grain instead of 6.
How about the saturant? How does that change the shear velocity? Well, not much. Since the volume of the grains does not change, the volume of the saturant does not need to change either. Only the shape changes, and fluid saturants offer no significant resistance to change of shape. So we have a picture of the shear wave passing through the rock from grain to grain solely at the grain contacts, with the fluid saturant not really participating in the wave. In effect, the fluid in the pores is just dead weight, to be dragged from side to side as the wave passes. As such, it affects the shear velocity only slightly, through the density rather than through the rigidity.
What if the pores also contain loose fines, loose clay particles? Well, if there are few, again, they make no difference to the rigidity, only a slight difference to the density, thus decreasing the shear velocity. And if there are many, a larger decrease in the shear velocity because of density, but the beginnings of an increase only when the fines really start to hold the grains in place, to resist their change of shape. Overall, not very much effect.
Except in those depositional or diagenetic situations that actually get clay into the contacts. Then the contact rigidity can come zooming down, and the shear velocity with it.
So let's summarize. What geological factors control shear velocity? The really big one first, cementation. The presence of cement swamps other factors. If the rock is not cemented, and only then, grain shape and grain sorting become major factors because of their effect on the flexibility and number of the grain contacts. So does depth of burial for the same reasons.
Now, the second-rank factors. Rock type. My goodness, look at that. The type of grain itself only of second rank. And the clay content. Small amounts of clay actually decreasing the shear velocity.
And finally, the minor factor, the type of fluid in the pores. Again, only because of its slight effect on density.
But one rock property that is not on the list is porosity. Not with any clear relation, and that's because, as we've seen, the pores do not really have much to do with it directly. It's the contacts that matter. Only insofar as porosity goes with grain type can there be any loose relation. And even then, just a little cement, having little effect on porosity, can have a dramatic effect on shear velocity.
Okay, now let's have a look at compressional velocity. As always, the same basic equation. Now, however, instead of just rigidity in the numerator, we have both the rigidity and the bulk modulus.
We remember why this is. When we apply the stress, the resulting strain involves both a change of volume and a change of shape. The reluctance to change shape is still the rigidity, as before. The reluctance to change volume is the bulk modulus. So both enter the compressional velocity.
Well, we can follow the same route. The cubic packing of spheres, as it participates now in a compressional wave. First, we notice something that is definitely different. That is, that in addition to the grains getting squeezed, the fluid in the pores gets squeezed also. Thus, in a compressional wave, it's not just the grains carrying the wave. The saturant contributes also. So while the saturant has little effect on the shear velocity, it may have a significant effect on the compressional velocity. In particular, we remember the presence of just a tiny amount of gas in the pore can send the compressional velocity down. And if there are few grain contacts and little cementation, can send it way down.
By the same token, fines in the pores have a different effect for compressional and shear. In shear, loose fine particles are just dead mass to be dragged from side to side, decreasing the shear velocity. In compressional, they make their own contribution to the reluctance of the pore fluid to be compressed, and so increase the compressional velocity.
Again, unless there is gas in the pore. But let's put the rest of that discussion in the manual and go on to the factors that are similar for compressional and shear. In shear, we have said the grains change shape, but not volume, and the contacts are critical because they oppose those changes of shape. In compressional, the grains change volume. The contacts are again critical because they oppose this change of volume, forcing the grains to change shape also, to bulge into the pores.
And all the things we've said about the contacts for shear apply much the same for compression. Overburdened pressure broadens and stiffens the contacts. So does cementation, and pressure solution, and so on. It's all much the same, and the potential for changes of volume and changes of shape is reduced if we increase the number of contacts per grain.
Okay, now let's go back to thin sections and to our attempt to visualize velocity geologically. In particular, let's see if we can find some way of expressing that ability of the contacts to oppose both changes of shape and changes of volume. A way that includes not only the broadening of the contact under overburden pressure, but also the effective broadening by cementation.
Well, my suggestion would be a measure like this: supported grain surface over total grain surface.
Well, maybe. Supported over total. Yes, maybe that would do it, until I can think of something better.
This, then, would be a master variable, expressing the contact properties of the grains. This would be the link between the thin section and the seismic velocity.
Okay, let's see how it would work. The shear velocity would depend, first and foremost, on your master variable, supported area over total. Then it would also depend, of course, on the intrinsic rigidity of the grain material, but not on much else.
Right. While the compressional velocity would also depend on, let's say, the same master variable, plus the same rigidity of the grain material, plus the bulk modulus of the grain material, plus the bulk modulus of the saturant.
Well, that's a simplification, of course. Both velocities are modified slightly by density effects, but it certainly is helpful. First, because it gives us that link, allowing us to visualize what velocity means in thin section. And second, it points the way to go if we want rock type from seismics.
Exactly. For if we divide compressional velocity by shear velocity, Vp over Vs again, then, to a first approximation, we eliminate the rock fabric, and we eliminate the rigidity of the grains. Indeed, in any situation where we know the saturant is water, we identify the rock type by the bulk modulus of its grains.
And the rock type, of course, was one of our objectives on the wish list. So to the extent we can measure Vp over Vs, we have another way to get rock type, to supplement that from seismic stratigraphy, and a much more positive way than from compressional velocity alone.
Whereas, if we turn again to the saturant, compressional velocity alone is the key to detecting the presence of gas, thus supplementing the message from burial history. So if we have Vp over Vs in the reservoir below the spill point, and another measurement above it, then, in principle, we can eliminate the grain material and be sure whether gas is present or not.
Though without ever being able to say whether the gas is commercial or not.
So finally, if we know the saturant and the grain material through its bulk modulus, we also know its rigidity, and so can get a measure of the master variable. Now, the master variable, whether we use this suggestion or some other, is not in itself a direct measure of porosity, or cementation, or diagenesis. But that does not mean it is not a very fair measure of the appeal of a reservoir. A rock with a low value must have a very open fabric, whether that openness derives from the grain shape, or the sorting, or the absence of cement, or shallow burial, or overpressure. And a rock with a high value must have poor permeability.
So, loosely, it is some figure of merit for a reservoir. Let's do this. Instead of separate items for reservoir properties, let's just put in reservoir appeal and give it a qualified yes.
So, standing back and looking at this list, I'm going to say straight out that there is far more geology in the seismic trace than just structure. Our challenge is to winkle it out.
Are we pretending that the geologist's wish list is all solved? No, of course not. Even the big ticks here are sometimes tough or need more extensive data. But the essential point is that the physics does allow the extraction of all these geological messages. We do have the tools. Where we fail, it is sometimes because of the geology, tectonic complexity, or because erosion has removed part of the picture. But often it is because of poor seismic quality or insufficient seismic resolution. And that is why we are discussing these geological matters here, so that all of us, field geophysicists, processors, interpreters, may see where the goalposts are before we specialize. In the field, we can jeopardize all of these objectives if the lines are in the wrong place, or in the wrong direction, or too short, if the group interval is too long, or the arrays are too long, or the spread is too short, if we do not plan in advance to measure Vp over Vs with a shear measurement or amplitude versus offset, if we use a source of inadequate bandwidth, and if we fail to get good static corrections from the first breaks, or the upholes, or a weathering crew. All of these possibilities can be lost forever in the field. Can be lost forever. You fellows in the field, you're important. The processors also must understand these objectives. We shall learn all the rules later, of course, but right now let's stress that different objectives need different processing. The optimum processing for structure is not that for stratigraphy. That for fault plane reflections is not that for stratal or unconformity reflections. And that for a gas-water contact is quite different again. Also very important is that geological thinking must go into the processing. Velocity picks and velocity smoothing must honor the stratigraphy and depositional environment evident on the emerging section. And the processing becomes more and more interactive. For example, we need velocities to get the structure right, and we need the structure before we know where to put the velocity measurement. Finally, the interpreter must extract all the geological messages in the seismic, harmonize them into an acceptable geological picture, forward model that interpretation back into seismic terms, and check that the result agrees with the original seismic data. So it really is a team effort. If you're the geophysicist in the field, let me never hear you say it. If you're the processor, think exploration objectives, not mere pretty sections. And if you're the interpreter, model it back. Well, there we are. The overall view, the grand view. From now on, we start to look at the details. The fieldwork first in the 300 series, then the processing in the 400, interpretation in the 500 series. In the 300 series first, you may care to look again at GP 301, Introduction to Fieldwork, then on to 302, 303, and so on. I hope you find it all as fascinating as I do.